right. Okay. So today I thought I would introduce this package, Statsmodels. So probably the most popular package for modeling, especially for kind of machine learning type applications, will be the scikit-learn package. But I would argue that scikit-learn is not really the best package if you wanted to do a traditional traditional stats modeling. Now, to be completely fair, I don't think Python is the best language for traditional stats modeling. So when it comes to traditional stats models, I think it's really hard to beat R. R being kind of the language designed by statisticians to do kind of stats work. But Python is very, very, very popular for machine learning applications. You have a lot of kind of libraries and packages designed for machine learning, and so scikit-learn is probably the most popular one, with kind of this wide array of models that can be fit. But there's also a whole bunch of others, such as TensorFlow and Keras, along with PyTorch and all kinds of other things for deep learning and things like that. And so Python is great for all of those applications, but sometimes you want to just fit a simple stats model, or fit a simple kind of statistics model like linear regression, logistic regression, something like that. And in those cases, I would say Statsmodel is probably the best Python solution. Okay. And so, again, I apologize. My notes today are, I haven't kind of polished them to kind of be in, what do you call it, slideshow format. So kind of my other ones are a little bit more polished. These ones are like semi-new content. And so you're just getting a Jupyter notebook here. And maybe at some point I'll polish them into slides that you can kind of flip through. But this is what we have right now. Okay, the documentation, always important, is right here. Unfortunately, stats models, I would say the documentation for stats models is not super great. Okay, whereas Pandas, I think, has great documentation. Base Python has excellent documentation. Stats models, it's okay. Stats models is like one of the times where I say, well, you might have more luck finding answers on a place like Stack Exchange or something like that. So finding answers there to see how do you get the job done for some kind of particular job. Whereas when it's base Python, sure, you can go to Stack Exchange and things, but I think the original documentation is probably your best resource here. Okay, so anyway, I'm just loading up a whole bunch of packages here. So kind of I got Numpy and Pandas and Matplotlib and Seaborn, which is all kind of important for regular data science applications in Python. And then we're going to load stats models, and there's kind of two forms where you can interact with stats models. One is the base Statsmodels API, and then the other is the Statsmodels Formula API. The Statsmodels Formula API is intended to kind of allow you to interact with stats models in the way that you would interact with, similar to R's formula notation. So when you create models in R using LM, you might do something like y tilde x. Excuse me one second. Okay, so the formula API, and API here just means the way you interact with it. Okay, API just means how you're going to interact with the stats models code. Pretty much everything is an API, but here we're just going to say, all right, we want to interact with stats models using the formula. The stats models API, the base kind of API is you use Numpy notation or array notation, and I'll explain what that looks like in a moment. Okay, so I'm going to go ahead and run that. And okay, it looks like all of those packages loaded. Okay, so here we're going to just start with a very, very, very minimal ordinary least squares example. I've got 4 pairs of points, 1, 2, 3, 4, and y is 2, 6, 4, 8. And so let's go ahead and create that plot. Okay, and then in here I've got plt.scatter. We're going to make a scatter plot of our x and our y points, and this is basically it. I've got 1, 2, 2, 6, 3, 4, and 4, 8, and we want to fit. Let's say we want to fit a linear regression line to this. Okay, so what I'm going to do is I'm going to create a pandas data frame using this this vector x and this vector y. Okay, so I'm going to just I'm going to do pd.dataframe, x is x, y is y, and let's print that out. Okay, so here it is. Okay, so we've got 4 data points, 1, 2, 2, 2, 6, 3, 4, and 4, 8. Okay, so if you know, we could see what a fitted line might look like using Seaborn, and you can do this. And let me do ci equals false. So this is kind of what a fitted plot would look like, and you get this line. And we could, if we wanted to, here, let me do a couple other operations here. So I've got x and I've got y, so I can do numpy.mean of x and numpy, oops, y, and then let's do numpy.standard. That's standard deviation. That's not right. I can't remember how to do standard deviation in NumPy. It is standard deviation, but we want the standard deviation of 1, 2, 3, 4 should be is not 1.18. What is hold on. Am I going crazy here? I'm so sorry. Should be 1.291. If I check an R. So why am I getting this? I think we're dividing by n rather than n minus 1. Oh, okay. The argument is DDOF equals 1. Okay, there we go. All right, and then we'll do all right. There's no core. And I can't remember any of my comments. Correlation coefficient, gosh. Like it's so hard to sometimes switch between using R and Python. You just, as you can see, standard deviation, STD, and correlation is core coefficient. Okay. All right, here we go. And then so your slope, if you kind of slope is U1 is equal to R times standard deviation of Y divided by standard deviation of X. So we'll do 0.8 times this divided by this, right? Okay, so we get 1.6. So this would be the slope, and then the intercept. Bar minus, so this would be Y bar being 5. It's 1.6. So we get intercept of 1. This is the slope, intercept, and whatnot. Okay, so this is what we have, and this is kind of just our manual work as far as fitting a simple linear regression model. Okay, well, what if we wanted to use stats models to kind of get this? Okay, so we're going to do statsmodels.formula.api, and for ordinary least squares, we could use smf.ols, okay, for ordinary least squares. And then we're going to specify y tilde x, okay, in quotes. And we're going to do data comes from D being this data frame that we've created earlier. So we're going to say, take the y column, explain using the x column, and we'll create the model there. If you say, let's print the model, you just get this linear model.ols object, okay, which is not very helpful. You also, it's not going to bother figuring out these coefficients. So it creates a model, but it doesn't actually try to fit anything to the data until you call .fit, okay? And then when you do this, then it will go through and calculate the coefficients. And so here we go. And then, and so finally, if you want to get the results, okay, we'll call results.summary. I think that's its content there. Okay. And so for results.summary, this is what we get. What is this? Okay. Oh, all right. Here it says the test is no good because we only have 4 data points in our I guess one of these tests, the omni-norm test, omnibus, I'm not sure. Okay, but anyway, what we see here, it prints out a whole bunch of stuff, right? The intercept and the slope, okay, the coefficient that corresponds to x and the intercept are given by these values. So the intercept is 1, the coefficient that corresponds to x is 1.6. It also gives us a bunch of values to determine, what is 1.0 a statistically significant value, and here we get a p-value of 0.7, so probably not. Is the slope statistically significant? And we get a p-value of 0.2. And even though our correlation is 0.8, it turns out that statistically speaking, this correlation coefficient is, and the slope associated with this may not be statistically significant, probably because in particular, because we only have 4 data points. And so when you pick 4 random data points, it's possible to end up getting a correlation coefficient of 0.8 just by random chance. Now, if we had more data points, our correlation coefficient would become more significant, our p-value would drop. Okay, here is the confidence interval for what the slope could be. Here's the confidence interval for what the intercept could be. Okay, we also get a few other things, right? It just prints out some basically number of observations, degrees of freedom, residuals, degrees of freedom for the model, three degrees of freedom total, right? And then you get your R squared, which is just going to be our correlation coefficient of 0.8 squared. And then, you know, other things, your AIC and BIC and things like that. Okay, I'm actually not sure what all of these other things are. Durbin Watson, does anybody know what this is? Let's see, what is this? I'm not sure. Okay, apparently these are values that you could calculate for a linear regression model. But that's this is kind of the output there. All right. If you wanted to, you could you can create a plot using the fitted line. So you can call statsmodels.graphics, and you can create a .ab line plot, and we'll use the results that that we created here. So we fit the model earlier, and we save those results as results. And so here, I will combine the AB line plot along with just a scatter plot of our data. And there you go. There is our data, and it looks very similar to here, but with a regression line added. Again, similar here, it's just our X limits and Y limits are ever so slightly off here. Okay, so we have that. If you want to get an Anova table for your results, you could do that as well. And so here is the Anova table. So here we have an Anova table for kind of our source of variation being X, which with 1 degree of freedom, the sum of squares, your F ratio, and the corresponding p-value, which matches our p-value for correlation coefficient here. And then, you know, residuals, you got that. Okay. And then if you wanted to use make predictions using your model, you could kind of give it new values here. And here it says, you know, our prediction for, say, if we plug in 2 for X, would give us the number of 4.2. So that's on the line would consist of 4.2. All right. Does that kind of make sense as far as just fitting a basic model here? Let me go ahead and give you your first view quiz answer for today, which is the letter B. B as in bear. B as in bear. B as in bear. Okay. We have NumPy array notation, and NumPy array notation is similar to scikit-learn's notation, and this is kind of the way, I guess if you were to try to fit matrices and whatnot. And so here right now, when we created, so going back to kind of our vector, not the data frame that we created, but just our vector. We have the vector X and the vector Y. So here X is just this, or I'm sorry, not vector, NumPy array. So we have this NumPy array for X. So X is 1, 2, 3, 4. And what we need to do is we need to kind of turn this into a matrix with a column for each kind of coefficient that we need to estimate. And so if we are fitting a simple linear regression model where we need to fit an intercept and a slope, okay, what we want to do is we want to basically turn this into matrix notation for linear regression. And I think you are familiar with this, where y hat is going to be the matrix B beta, your coefficients matrix, and multiplied by X, right? So something else, but so so here we want the matrix y hat, this is going to be equal to kind of our matrix beta times our matrix X, okay? And our matrix beta, well, is, okay, so our X matrix is going to have a column of basically values, one values, and then we're going to have a X1, an X2, an X3, all the way to an Xn, and our matrix here our matrix here is going to be beta 0, beta 1. Okay, I guess those dimensions don't line up, do they? Right. So this would actually be I think I have these swapped. XB would be our XB is our, sorry. Okay. I gotta fix that. Okay, so we have our X matrix multiplied by our coefficient matrix beta, and this is what we're going to get. And so when you y1 will equal beta 0 times 1 plus beta 1 times x1, okay, or y1 hat, let's say, and so on and so forth. All right, so to get x to work, we have to add this column of ones here. We're going to add a column of ones, and so now x has a column of ones added to this column of 1, 2, 3, 4, and then to fit a model here, we're going to say fit a model between y, and it's fine. Y is just that array. Y is just this array 2, 6, 4, 8, and we're going to fit the model using predict y based on x. Using statsmodels.ols, we can ask to fit it, and then we get the solution, and we have exactly this. Okay, so the constant, the coefficient for the constant is 1.0. The constant for the kind of first value here, x1, is going to be 1.6. In ordinary least squares, you can take your matrix X and you can find your coefficients by doing X transpose X inverse. So here I got X transpose X, and then we'll take the inverse by doing np.linearalgebra.inverse multiplied by X transpose Y, which is given by here, and it gives us this this matrix 1, 1.6, which matches what we have here. All right, so you could do this. Okay, let's try maybe a sort of a semi-real example. I don't know if this is any more real than the, the examples we've been doing here. So here is there is a data set, and this is for the this is Olympic race times. The race times gold medal time for the Olympics 100-meter dash. Okay, so the men's 100-meter dash, what was the winning gold medal time? And I guess the first Olympics were in 1896, and then we look up to 2012. And so the very first time it was held, the winning time was 12 seconds, and then we had 11 seconds. And then with the advent of stopwatches with slightly more accurate values, we got 11.2, 10.8, 10.3, and then we started being able to record to the nearest hundredths of a second, and that's only been for, I don't know, a handful of years here. Okay, so anyway, if we wanted to just see what this looks like, this is kind of what the dots look like. And so we can see just as time has gone on, the winning times have gotten faster and faster in general. Okay. All right, so if we wanted to, so here are the commands for fitting the models. And so in this case, we have year and time stored in the data frame. And so we want to predict the time based on the year. Okay, so here I'm going to just do the formula API. So Statsmodels Formula ordinary least squares. Data comes from the Olympic data frame. Then we'll fit the, we create the model, we'll fit the model, and then let's print out the summary of the results. Okay, so these are the regression results. We get a correlation coefficient of 36.3, which doesn't really make sense in context. I guess that would be the winning race time if we extrapolate it all the way back to the year 0. So I guess during the Roman height of the Roman Empire, if they were to have a race, did the Olympics exist back then? I don't know. In Athens, Greece is when they had the first Olympics, and I don't know when those were. But anyway, yeah, it says the winning race time would have been 36 seconds, and I don't think that would be true. Did they even have the metric system for measuring distances? Who knows? Okay, but anyway, it doesn't make sense to extrapolate back to the year 0 here, right? So it's just kind of if we wanted to make a prediction between these kind of posts, right? And if you were to extrapolate far into the future, we would end up having a race time of 0 and negative values, which again also don't make sense. But basically, at least for the century of values that we've recorded, it says each year our prediction for the speed drops by a little over 1/100th of a second. So every 4 years we're dropping by around 5/100ths of a second, our prediction. That's kind of what we have here. Okay, so so that's that. And if you wanted to plot this, we could do that here. And so we could see the line fits here. We also see, here we've got a bit of an outlier, Okay. And we have that. To be honest, I'm a little bit rusty using stats models as far as fitting basic linear regression and whatnot. I would primarily use R. And also, to be honest there, I don't know how often I fit linear regression models other than for teaching examples. So, here, if we want to use the Statsmodels API, okay, we're going to take that column, Olympic.year, and we need to add a constant to it. So we're going to do Olympic.year, add constant, and so this will create our array using years, our years array, and then we'll fit the OLS model between the time array and the year array. We ask for it to fit the model, and we ask for the summary, and then here we get the same values. Okay, just here we get the coefficient for year, and then we get a coefficient for the constant. We could have prepend true or false, it doesn't matter. Prepend true would put the constant in the front. Okay, so we have the constant at 36.309, matching exactly what we have here, and then the coefficient for the year, negative 0.132. Okay, so we have that. We're going to finish a couple minutes early. I'm going to go ahead and give you your second view quiz answer, which is the letter C. C as in cat. C as in cat. Okay, so in this case, what is the p-value for our slope? The p-value for our slope is pretty much 0. So it's our test statistic, our t is -11. So it's 11 standard errors away from the mean. So we have a p-value of pretty much 0. And if we create a confidence interval, we're quite confident that whatever it is, it's negative, somewhere between 0.011 hundredths of a second each year for each year that passes to 0.016 seconds faster for each year that passes. We'll get an r² value of 0.826, so on and so forth. Okay. And so these are all kind of the values that are useful as far as trying to fit a linear regression model. Here I thought maybe we'll do a logistic regression example. And so for this, I have this fictional data set that it shows a potential relationship between age and congestive heart disease. This is not real data. It's made up, okay? But the data set has a column, one column for age, one column for CHD. CHD is recorded as a 0 or a 1, as whether somebody had heart disease or not. Okay, and what we're going to do is we're going to turn the CHD column from an integer into a categorical variable. So I'm going to use pandas.categorical. This will indicate to pandas that this is a categorical variable. We're reading the data into CHD. So here, let me just show you what CHD looks like right now. It's got this age column and this CHD column. And right now, the data types, these are both integers. But what I'm going to do is I'm going to turn the CHD column into a categorical variable. And when I print it out, it looks exactly the same. But when I ask what are the data types, it will say that coronary heart disease or congestive heart disease is categorical now. Okay, and so to kind of plot this rather than a scatter plot, I mean, a scatter plot could work. It's just that with the overlap, it's hard to it's hard to see because the dots overlap. Maybe I can do, say, alpha equals. You get a little bit of a sense here of where the dots lie, with kind of some more concentration over here and less concentration, or more concentration down here. The swarm plot from Seaborn might be a tiny bit more useful in that we can say, okay, there's more points down here for zeros, okay, and then for ones we got more points up here, okay. So we can see the difference in density of the plots over here. Okay, so how would we? And then Seaborn also has a logistic regression plot. And so you can say Seaborn regression plot, X is age, Y is CHD, and you can just specify logistic equals true, and then it will try to fit a logistic regression plot. If I were to remove this, then it tries to fit a straight line, okay, and we know that that's just not going to work. So here, turn it logistic, and now you get kind of a logistic regression curve fitted to the data. Okay, well, if we wanted to fit this, we'll add a constant to the age variable. So basically, as far as formulas go, all we're doing is we're taking this kind of thing and we're just applying a logit transform, right? Not copy that cell. So basically all we're doing is we're doing Logit transform. So we're just going to do XP of 1 divided by exp raised to the, it's the negative of this, right? So if you take this thing and so we take raise this to the e to the negative this kind of this linear regression thing, and we're doing that. Okay, so here we're going to add a constant, just kind of like this, and then to fit the logistic regression model, we'll do statsmodels.logit, and then we'll do kind of predict CHD based on the array created for age. And it says, okay, it figured it out. We'll print the summary here, and we get coefficients for the age as 0.1109. Okay, so what is that? What does that mean? Well, for logistic regression, this is your change in log odds is what this represents. Okay, and if we were to fit a, say, a scatter plot, you know, here's the scatter plot, and then we could kind of create the fitted line between, say, the age values and our predicted values. Okay, and this shows up here. So let's say so if I take if I raise the slope value, hold on. Oh, never mind. Okay. But anyway, that's this is how we would fit, say, a logistic regression model to some of these things. And then again, you could read the documentation for, you know, when you do regression, you can also get kind of all of your diagnostic plots as far as, you know, are your residuals normally distributed, you know, say for something like this, if we want to check if our points are normally distributed. But yeah, you'll have to turn to the documentation or other resources online to look up all of those things. But yeah, this is Statsmodels. I would say this is what the tool that we would use for kind of classical statistics modeling in Python. Next week, probably what I will introduce a little bit of stuff from scikit-learn with just some kind of basic things for, I don't know, just an introduction to some machine learning concepts and ideas. And, you know, this is not a machine learning course. And so I hesitate to teach you too much because I don't want to just say, here's some tools, you know, like, oh, this is how you use a chainsaw. And then you do something wrong and create disasters or something. So, but we'll take a look. Let me talk, and then yeah, next week I'll also give you a better idea of what you can expect for the final exam. The final exam is scheduled for Monday of finals week, and I've decided it's going to be online. We'll take it over Zoom, and I will cover probably up through the week 8 material. So up through week 8, which was object-oriented stuff, I will not cover content from week 9 or week 10. So week 9 was SQL and stats models, and next week will be scikit-learn. So we'll cover it up through week 8, which object-oriented stuff in Python, pandas, Numpy, some data visualization, all of those things. Okay. With that, we'll end here for today, and we will see you on Monday. So have a good weekend and see you. Oh, I need to give you your last view quiz answer. Last view quiz answer is D. D as in dog. D as in dog is your last view quiz answer. Okay, all right. Well, thanks everyone. Have a good rest of your day. Have a good weekend. We'll see you on Monday.